Thank you, Emanuele, for your introduction. Thank you, Marta, for the invitation. Thank you, all the organizers. I'm very pleased to be here. Good afternoon, everyone. I know this is the last session of this track. There's a cocktail, I think, waiting after this, so thanks for being here. I'm going to talk about some use cases that we have at NG, and in the context of a large organization that provides energy to multiple types of customers. So I'm a Chief Data Officer at NG Digital, which is the software arm of NG. When people ask me, how does AI help with the energy transition, I try to come up with various concrete examples. So it can be, for example, trying to match energy production to the load profile of consumption patterns. It can be trying to optimize the production of renewable energy in the energy mix. It could be trying to track and identify patterns of consumption. For example, when you're in the UK and you have a football match, it's known that at halftime there's a peak of energy consumption due to everyone switching on their kettle for making hot tea. So things like that. How can we use information from the environment, the organizations we work with, third-party data suppliers, to build software both for internal use and for our customers. So NG is a large utility company. We provide services in over 70 countries. It's more than 100,000 employees worldwide. And we ride on the wave of mega trends that we've identified in the market. They're not specific to us, but it's things that we've observed in terms of decarbonization, in terms of decentralization, and various energy consumers now source their energy either locally or through third-party providers, besides the national grids. And then there's the explosion of digitalization. It's software, it's data, it's IoTs, it's edge computing, it's AI. It's a variety of tools that we can now leverage to help with providing digital transformation and change to the energy sector, which is an old industrial sector that's in need of change. So I'm going to talk about various use cases, 4 practical applications that we have in 2 categories, both operational efficiency through predictive maintenance. So I know we've talked about some examples in cable predictive maintenance. I'm going to talk about it in the context of power plant and energy generation. And then I'm going to talk about energy efficiency and how we can use data and AI to help monitor, manage energy in large university campuses and large multinational organizations. So to start off, I'm going to talk about thermal power plants. So it may not seem very green. NG has a strategy where it sold off and shut down most of its coal power plants in the past few years. So our thermal power plants now are gas-powered. And the main reason why we need to do predictive maintenance on these power plants is not only for cost saving, it's also because the operation mode of these power plants has now shifted. Because we have more renewable energy sources in the mix, wind and solar, which are intermittent, we need to switch on and switch off these power plants much more frequently than they were designed to do originally, which introduces wear and tear on the equipment. That's very different from the usage patterns they were designed for. And we work both on the turbines, but also very specifically on what we call the balance of plant, which is types of equipment like valves, pumps, filters that comprise the rest of the power plant. So just a quick reminder, I know we've talked a little bit about this earlier, but where are we now in the predictive maintenance journey? So we started from reactive maintenance. I won't go back into the details there. But we have 2 types of operational efficiency measures that we take now. The first one is around smart conditional maintenance, which means that we track some conditions under which we need to change a piece of equipment. And instead of having those conditions hardwired because of some threshold that's hard-coded, we use machine learning to define those thresholds based on previous historical data. And the other approach that we have now is predictive maintenance, which is trying to detect deterioration of equipment. And sometimes in those thermal power plants, it's between 1 to 3 years, sometimes even 4 or 5 years ahead of time. Because we have to, what we want to try to achieve is to time the maintenance or the changing of an equipment to a planned maintenance cycle. And typically those happen every 6 months or so. So when the power plant shuts down, we want to make sure that we can change a piece of equipment that we identify is going to fail or be unusable within the next 6 months. Ahead of the game there, and things that we are starting to explore but we haven't industrialized yet, are around prescriptive maintenance and also command and control, where we can automate some of these actions. So very quickly on what's a combined cycle thermal plant look like, because we work a lot with people from the business, people who've been operational on the power plants for decades sometimes, and they provide us very valuable information. And the reason for this is that we need to develop data science models that include the business knowledge. We don't want to be black boxes, we want to be systems that are explainable, that can provide feedback to the users. So trust is a large part of what we need to do and embed in our systems. So here it's a combined cycle because we have both a gas turbine and a steam turbine. So the gas is burned using in order to power the first turbine, the gas turbine, and what comes out of the turbine is used as power, heating power, thermal power to heat up water into steam that helps power the steam turbine, and then there's a condenser that reduces the temperature of the vapor, and then it's then ejected in the air. Like I was saying, we have different types of use cases in this power plant, where we have different types of valves that we provide predictive maintenance systems for. So I'm going to go into one of the examples here, which is the TCV, the temperature control valve, which is what we call the desuperheater valve. It means that it reduces the saturation point of the vapor that goes into it before it hits the turbine. And the reason for this is to safeguard the turbine so that it doesn't have too hot vapor that would spoil the blades. And these, what's interesting to me, I've been with NG for the past 3 years, and what's interesting to me is that a lot of these equipment were instrumented maybe 10 years ago. So we have a lot of data to work with. So these industrial sites have SCADAs, have industrial tools that capture the data, and we're able to leverage all this data to create patterns that feed into the machine learning models that we want to train. So some of the anomaly detection and alerting systems that we have built on top of this data, we have health alerts, which give real-time information on how these pieces of equipment behave. And the physical threshold there are defined by experts. So we have business rules that tells us that if a certain signal that comes from one of the sensors exceeds this threshold, then there is a problem that we need to investigate. We also use statistical thresholds, where we have those models that are developed using machine learning techniques that help us detect failure ahead of time, so a few hours before that may happen. And then we've got future health alerts that are, like I was saying, 1 to 3 years ahead of time. So we explore different types of machine learning techniques to help with our tool. Initially, we started with an unsupervised learning technique because we weren't sure that we had enough training data, labeled data, because a lot of the logbooks that are captured in power plants are manual records that some of the operators and technicians write down on a piece of notebook, and they're stored and archived. And the effort to digitalize that is significant. So we wanted to try out some unsupervised learning methods that were unsuccessful. And then we decided to have a supervised learning approach that instead of having labeled data that told us when a piece of equipment was failing or when the power plant was shut down, would be based on business rules that were defined by the experts. So we have thresholds that are defined by for certain variables by the experts, along with the data scientists that track and visualize the data. So what we've been doing for each new piece of equipment that comes in is to have a data exploration phase with R&D, where the data scientists work alongside the business people, try to map certain variables, and then look at the data across the different maintenance cycles when some of the sensor data resets, and then look at how we can build a machine learning algorithm and train that model specifically for each piece of equipment. So because thermal power plants are custom made and very heavy investments with lots of manufacturers that contribute different pieces of equipment, they're not standardized. So there's a lot of R&D effort that goes into each piece of equipment that needs to be onboarded because we need to map each of the sensor values to the business rules that are applicable to that type of sensor value. So what we developed was a UI that's applicable and used by the business people. And we realized there that a large part of the effort in building a data science solution is, of course, in data preparation. We know that typically 80% of the time spent on a data science project is going to be on data quality, data cleansing, and data preparation. And we noticed the same when we build software, is that maybe 80% of the time that is spent in deploying the software is actually change management and helping the users include the software into their process. So one of the things that we've done is alerting systems, so people don't have to look at their dashboards in the control center of power plant regularly, but they get alerts on their mobile phones, for example, when there's something that need attention. And it's also interfacing the software with existing applications like SAP that they use to track maintenance and operations of their equipment. So we've talked about thermal power plants. What about wind and solar? So there we're interested in forecasting. We're also interested in predictive maintenance, but we're also interested in optimizing the production. So for example, in wind turbines, we look at how the yaw, for example, of the nacelle where that holds the blades for the wind turbine is positioned according to the wind direction. So that we can optimize the production of electricity from wind. We also look at things like in PV parks, if there's strings that connect multiple photovoltaic boards, that they're connected, because if they're disconnected, then it's a loss in production. And that happens often when there's wind or certain environmental activities that disconnect them or cut them. So we have multiple use cases in the renewable sector, and we have one particular application that does hypervision for these types of renewable energy sources. But typically what we try to do is to detect underperformance, because if we want to increase the mix of renewables in the general energy consumption that we have with different customer segments, we need to optimize how much we can produce from whether it's wind energy or solar or biogas, etc. So, for example, if we look at wind, we have two types of approaches that we have built. The first one is looking at a park of multiple wind turbines and looking at how neighboring assets behave compared to the one that we're exploring. So because the wind and the environmental conditions would be similar for all the wind turbines on a park, we can detect lower production in one of the wind turbines, or we can detect defects that some of these pieces of equipment may have. The second family of machine learning techniques that we have developed are causality relations between each of the sensors that we have in one particular wind turbine. So we look at vibrations, we look at different types of sensor data, and we see what the normative behavior would be and how we can detect deviations from that in order to be able to detect that something is going wrong or that we need to optimize. So generally, the approach we have is to include business rules to very simple and open box or white box machine learning techniques. And that's typically the baseline that we've had so far, so that we can predict values and define what the normal behavior is and what the predicted behavior would be for new types of equipment. But more recently, we've explored some neural network types of applications around anomaly detection, and that's an unsupervised model that we've developed software for in a proof of concept. And the goal here was to raise machine learning alerts based on abnormal behavior for certain variables that come from data captured by sensors. And that has multiple steps. So first we detect that there's anomalous behavior. Then we detect that what the root cause is, what needs to be done by the operators on the power plant in terms of operation and maintenance. And then we help the operators towards the resolution by saying that either a piece needs to be changed or some adaptation needs to happen in the way the power plant is managed. So the value that we bring through this application is to really be user-centric, to take into account the workflow that the users have in the power plants in managing the electricity that is produced by each of these wind turbines in parks. And we reduce the data science work because, like I was saying, if you have to do R&D for each piece of equipment, that's significant time and effort. So instead of that, we have a global detection system that can be deployed across multiple pieces of equipment that share certain characteristics, and that can be a large time-saving operation. So in terms of the machine learning approach that we have, this global anomaly detection is the first stage of a larger architecture and system. We have unsupervised global anomaly detection that predicts and gives alerts to the users. And based on that, we have rule-based failure detection mechanisms that are based on business knowledge that we then use to make recommendations to the operators in terms of what actions they can take to correct either for energy production or for maintenance of assets. And this machine learning pipeline is something that we've developed using only 2 years of historical data instead of the 10 years that I was mentioning earlier for the supervised learning approach. So now that I've talked about these two use cases in renewables and thermal power plants for the production of electricity, I'm going to focus on two other use cases that are related to the consumption of energy and the energy management in different types of customer segments. The first one is for institutions. So we have a contract with Ohio State University, for example, in the US, which is a university that has approximately 150,000 people on campus. If you count students, researchers, staff, and various people working, faculty, etc. It has dormitories, laboratories, it has stadiums. So it's a very large campus, almost like a small town. And we have a 50-year contract with them, and the first goalpost is to reduce their carbon footprint by 25% in the first 10 years. So like was mentioned earlier, there's a lot of energy savings measures that can be applied to buildings to reduce energy consumption. But we also use AI and machine learning techniques to track what the baseline would be. So very similar to what was described by the startup earlier. And we provide energy as a service. That means that the campus now outsources all their energy asset management and operations to NG in order to for us to keep the lights on and keep a comfortable level of temperature in the buildings. So for that, there are some capital investments that need to be done, like having local storage, battery storage, for example, local power plants for local generations using PV or cogeneration plants. Also purchasing of PPAs or power purchase agreement to buy green energy instead of buying from the grid. So various types of mechanisms can be used. And we also track the energy consumption in buildings. So for that, we have data that comes from meteorological data providers. We also use occupancy data. And for that, we track, for example, the number of connections to a router in Wi-Fi in buildings to have a proxy view of how many people are in the building at a given point in time. And then we can control the systems, provide feedback to the operators, do demand response type of events, to be able to track what the reduction in carbon emissions due to reduction in energy usage over time. So within 3 years, there was a 10% reduction in carbon emissions and energy usage that should carry on to reach our goal of 25% and be net zero within the next 20 years. And what's interesting in this application is that the front end that's provided by the application is available both to operators within the university campus to track and manage their energy sources in buildings and various locations within campus. But we also provide the data to researchers, and we provide a public user interface to students to be able to track their consumption within their dorms, for example, gamify the experience, and have behavioral change to be able for them to track how much energy, for example, their dorm or their lab uses, compare it with other entities within campus, and be more conscious of how much energy they use in their daily life. So here some examples, and I won't go into much detail here in terms of what are the types of use cases we have in this Smart Institutions application, with a variety of data sources that we leverage to be able to do forecasting 24 hours in advance in terms of how much resources we need. We also have explored different types of frameworks. For example, instead of doing one single predictor that would give us a prediction for the next 24 hours, we have, for each hour, we have a separate predictor for 48 hours. So that's 48 different predictors. And that takes into account, for example, nighttime versus daytime and things like that. And one of the use cases that we've developed is around measurement and verification, which is to create scenarios that look into the capital expenditures of the university in terms of a certain capex amount that they can invest in either insulating buildings or changing lights into LEDs, or purchasing a new energy contract, or building a power plant on a local site. So each of these investment decisions, the goal there is to be able to predict what impact it will have on the energy usage and the carbon emissions over a period of time, to be able to help them make those decisions in a data-driven way. The final application that I'm going to talk about is called Ellipse. It's decarbonization software that's available to multinational corporations. So this was launched at the end of last year. And the goal there is to enable organizations, so large organizations that have sites in multiple countries, that have office buildings, industrial sites, a large supply chain as well, to not only measure their baseline carbon emissions, and that often is done through third-party suppliers or consultancy that ENGIE can provide, or other providers can work with them to develop, and it's part of their ESG reporting requirements very often. But also to define what the targets should be, and then to track their targets and to track their actual emissions according to the targets over time, and break that down according to geographies, according to different types of topologies, whether it's office buildings versus industrial sites, and then track their goals over time, so that when a company says that, by 2040 we'll be carbon neutral, we'll be net zero, where are we today, and are we on track to reach that goal in the next 20 years? And for that, of course, a large part of the platform is based on data science use cases, mostly around forecasting, because we have to track the baseline. What would be the carbon emissions and the energy consumption had we not done anything? And what is the estimated savings that we have over time for the foreseeable future? And how do we achieve net zero? So there are various steps in doing that. It's building a robust baseline that can be trusted, and that's a topic that we discussed earlier today. It's also defining targets that are science-based and data-driven targets. It's designing projects that are cost-effective and can help decarbonize the most, have decarbonization projects that are the most optimized in regards to cost, time, and effort. And then track progress according to various breakdowns in the organization. So for example, if it's an MNC, at the headquarter level, the executive committee level, we want to have a global view of where things are headed, but we also want to have operational data so that regional managers and sustainability managers at local sites can take appropriate actions to, for example, change a boiler because the efficiency is lower than their neighbor's boiler, for example, and use different types of mechanisms that they can use, that they can track the targets and achieve their local objectives. And the final goal here is to encompass as well scope 3. So a large part of the scope 3 emissions are based on supply chain. And the Ellipse platform also provides services to track using various types of different methodologies, depending on whether we have data from the suppliers or we don't. We track what the carbon value of your supply chain is and how can you optimize that, not only for cost, but also for the different strategies you can have to reduce scope 3 emissions. So thanks for your attention. And just a last word on the fact that we believe that it's my strong conviction that the decarbonization journey is a long one, and no one organization is going to get to it by itself. So it's an ecosystem. We need to be working together between academia, startups, large organizations, and the public. So you're welcome to contact me for any collaboration opportunities, and thank you very much.
Since I have the mic, maybe I allow myself a question. Just very quickly about the wind performance. Mm-hmm. You mentioned that you can compare, some wind turbines to others and so on. And I just have a curiosity question regarding the time scale at which this makes sense, right? Because as much as two wind turbines may be similar, and if they're closely located, they may have similar wind conditions. They're still like sort of micro. Local changes and whatnot. So at what time scale does this performance comparison make sense? Is it more like hourly, daily thing, or more like monthly, yearly comparison?
Yeah, we get two types of data. We get real-time data and we get cold data. So for comparison purposes, we do it at, we have multiple time windows that we use, but typically we do it short term, so within a day, from minutes to hours to within a day. And the larger scale comparisons are used for defect, identification.
Thanks.
Okay, regarding predictive maintenance, how do you validate your models? Because if they are right, then you replace the elements that potentially will malfunction, and you don't have the data to validate them. So how do you do it? Yeah,
it's a tough problem, and thanks for asking that. What we do is typically work with the experts, because before there was predictive maintenance solutions, the experts would go on site and do manual work for several days to identify what the behavior of a piece was and would it need to be changed or not. So we won't wait for 3 years before a piece breaks. But at the moment, what we're doing is validating with experts to be able to speed up the process of validating an equipment. So yeah, the validation question is a tough one, and it's also linked to the question of how much value can a solution bring, because it's all potential value. So how much is a power plant willing to pay for a solution that predicts something versus, so what we typically do is, identify the number of breakages that can happen on average within a time frame of a year, a couple of years, and say that, if it's an unplanned breakdown, this is the amount of money that you would have lost because of loss of production and penalties. But that's about it.
Okay, thanks. That was actually my second question. So you're also a live company. It seems that you are solving all the problems.
Yeah, I think that's the interesting thing about these use cases, that they're in production. We see that a lot of the data science we do is not the state of the art, because the larger problems we have is how do we get it into the hands of the user, and how do we make sure that there is some impact.
Other questions?
Yes, thanks for the talk and the great wealth of information. I have a question regarding the predictive maintenance. As you said, change management is one of the biggest issues, and as a data scientist, we may have a lot of trust in the models and the alerts that it gives, but maybe the plant operators don't have that much trust. Maybe they're used to expert thresholds. So what's the strategy to make sure that they actually use the alerts from ML system with as much trust as the ones from experts?
I think that's where my startup experience comes in handy. We work in a user-centric design thinking approach, where we include the users from the beginning of the process in order to understand what their workflow is like, what are the pain points, what would help them make better decisions, both for them and for their employer. And we work with them through the development of the solution. So we started this solution, which we call Robin Analytics, for the predictive maintenance of power plants 2 years ago. And it's taken that amount of time to be continuously talking to users and have them trust us, because relationships get built over time. And it's a very human problem that we need to solve along the technical problems we have.
Great, thanks. I have a second question, if I may. More of a technical one. You showed also that you had a model that builds correlations and causality between sensors.
Mm-hmm.
In this case, do you build causality graphs from expert knowledge and then use data to tune it or train it, or can you get causality graphs from data in a data-driven fashion directly?
I think I'll have to take that offline, because I'm on the data officer executive side and less on the data science side these days. I've gone to the dark side of the force. So I'll have to put you in touch with my team for that.
No problem, thanks.
Any more question? Yes.
Thank you. Great talk, thanks. With the Ellipse platform, you mentioned that you provide some estimates of the impact of some initiatives on reduction of emissions. How do you calculate that?
So we have a set list of projects that we can have. A lot of it is still done manually. So we get data from, so NG has a consulting arm that we will leverage. So a lot of the data that we have from this consulting arm are being incorporated into the Ellipse platform now, so that over time we can productize the approach. But at the moment, it's still on the verge of shifting from a one-on-one, ad hoc approach to a productized approach. Yeah.
Makes sense. Thanks.
Okay, so I have maybe a last question, both for Rafal and for Mihir, our two keynote speakers. So can you share one piece of advice for our young researchers and one piece of advice for startups?
Okay. I got the back of you for a second. No, okay, I can share one piece of advice for startups in research, let's say. So, starting researchers. There was a question. I don't know if the lady's still in the room, asking how can we compare models from different papers? Oh, that was you. Okay. Don't do it. That's my advice. It just doesn't work. I mean, the only way to compare it is you need exactly the same data set, exactly the same calibration windows, and exactly the same test windows. Otherwise, forget about comparing results of errors from different papers. It's just useless.
What about are you trying to control for difference in, for example, the forecast horizon and
No way. I mean, you can do the experiments yourself, then of course it's okay. So, but then use exactly the same data sets, exactly the same setups. Then you can compare different models. But if you look at different papers, the people do not write what they have actually done. Okay.
I can confirm.
My advice to researchers and people working in data science generally would be, if you can avoid doing data science, avoid it. Solve your problem, regardless of how you do it. And once you've proven that solving the problem is useful and AI can help in scaling your solution, then do it. Even if it means doing it manually behind the scenes. Many companies have proven that it's a useful approach. Do that, and then I tell my data scientists to solve problems first, and then do data science if it makes sense. The advice to startups is maybe a partner, right? You're going to get up to a certain point on your own, but you're going to get leverage and address a larger market and have more impact if you have partners to work with. So I think that's my advice.
Is that an invitation to Electricity Map and Inno?
Absolutely.